You open. Our seminar this year is a lecture by Alexei Kotov. He should speak about the graded simple Hopf algebroids. Yes, so that's
Thank you very much. So it's nice to be here. So I hope that finally we'll come to algebroids because it's a kind of, I mean, the topic which I want to touch in this talk about Harish-Chandra for algebroids, it's really not known. Well, algebroids are known, and there are two kinds of algebroids. In fact, I will try to explain what's the difference. But I will start with the better known things. So this is the topic, graded super-Hopf algebroids, and it's based upon 3 papers with Vladimir Salnikov and Benoit Joubin and Norbert Pansan, third one. The first one is actually the basic reference that was published in the Journal of Geometry and Physics last year. The second one, which is somehow gives the background for the first one, it was published in this year in Differential Geometry and Applications. And the last one, the origin of the whole series, it's a joint paper with Benoit Joubin and Norbert Pansan from Luxembourg, which was published in Transformation Groups 2 years ago. So the plan of the talk is the following. I will start with known things, classical things, with algebras and Hopf algebras. It's a reminder because, well, I will show what it is, but was it known in many textbooks. Then I will show the inverse enveloping algebra as an example. Of course, it's also very well known, the Poincaré-Bergov-Witt in a certain form which is suitable for the rest of the talk. Then I will discuss a little bit the Z-graded case. And actually, all this, the idea why we started doing Z-graded case was somehow motivated by the third paper joined with Benoit Joubin and Norbert Pansan about integration of differential graded Lie algebras. And we figure out that it's easy to do for n-graded manifolds. But it was a kind of question, not really a hard problem, but a question what kind of functional spaces are needed in the Z-graded case. And then we developed this in the second paper and applied here. So I will tell you why Z-graded case is actually simple. Then I will remind you also the integration of pairs of Lie algebra and Lie subalgebra by use of Harish-Chandra pairs, and it's one of the main approach to supergroups, for instance. And the last one, I hope I will be able to touch a little bit the Hopf groupoids and tell you what is known about Harish-Chandra pairs for them and what is desirable to be known. Okay, so let me start now with Hopf algebras and bialgebras. Well, of course, everyone knows what is an associative algebra. It's a space together with multiplication. It can be viewed as a map from the tensor product of H and H to H. If it's a unit of algebra, there is a unit. I assume that for simplicity that everything is over R. So it's a map from R to H, can be some other field, or a ring if it's over a ring. And then there is a unit law. I mean, the multiplication satisfies the unit law. Here, what is written here is just functorial way of saying what everyone knows, right? So if you multiply with the unit from on the right or on the left, we get the same element. And also the associativity. Here, what is written here, if you apply this composition to 3 elements, it will mean that the first take the product of the second, the third, then with the first one. And it's the same as the first 2, and then with the third one. It's a functorial way, again, to say about the associativity, knowing from the kindergarten. So, but then also, it can be some other structure. If you try to dualize the notion of an algebra, we come to the notion of a co-algebra. So if the multiplication, when the multiplication is a map from H cross H to H, the co-multiplication should be the dual map, right? So you can assume that this is actually H star, right? So it's a map from H to H, tensor H, which is probably also the completed tensor product. Then a co-unit is a map from H to R. Sometimes it's also called augmentation. And then also, if you have these two maps, two structures, which are compatible by use the associativity and co-unit laws, which is exactly the dual version of the first two, then we say that there is a bialgebra or co-unit or bialgebra. Now, if we combine the first four, I mean the 1, 2, and 3, 4, in a suitable way, so we require the multiplication is in a co-algebra morphism and co-multiplication is an algebra morphism. Then what we'll get will be a bialgebra. So it's an algebraic it's a space together with two algebraic structure, the product and the coproduct, also with the unit or co-unit, such that everything is compatible. Then there is a simple example of such a structure, which also leads to another another structure, which is called antipod. So suppose we have a Lie group, suppose we have a group G, and take as an H the space of functions, the algebra, commutative algebra of functions on it. Then in the group there is a map G cross G to G, which gives us precisely the co-multiplication here, right? So it gives us a map from Fg to Fg cross. Sorry. Yeah, right. F cross G, which is the same as Fg tensor product, the complete tensor product, Fg and Fg. Then also there is a multiplication of functions, which gives the multiplication. So this is the co-multiplication. If you take H equals to Fg, so this gives a natural co-multiplication. This gives a multiplication. Then a unit in the algebra of function, just one, gives you a unit. So just one is a unit in H. The neutral element E inside G gives you a co-unit. So just evaluation, the neutral element gives precisely a map of this form. So it will be the map from H to R, right? All the augmentation. And then there is also another operation in a group, which is the inverse, which sends G to G inverse. And this map generates another map, which is called antipod. So it's a map from H to H. It also satisfies certain axioms, which you can easily derive just from knowing how it works for a group. It's nothing special. So in this case, we know that the algebra of functions on a group is naturally commutative. The co-algebra is not commutative, is not co-commutative. It means that if you apply first delta and then exchange argument of two arguments in the tensor product, it will be not the same, because in general a group is not commutative. If it's commutative, then the algebra by the result of this all compatible operations, which is called a Hopf algebra, will be called commutative and co-commutative. In the case of a usual of a group, we obtain a commutative but not co-commutative group, Hopf algebra. And there are also examples, which I will not show here, but there are also examples coming from quantum groups where the Hopf algebras are neither commutative nor co-commutative. So both properties are violated. There is a well-known example. Can I also use this one? Or do you think it was too far? This. Yeah, can I use this pieces of the blackboard? So yes, and now I will give a good example, which is also very well known. And this example is called the universal enveloping algebra. Actually, it's related to a certain group. I will also tell this. It's a universal enveloping algebra of a Lie algebra. So suppose G is a Lie algebra. Then, well, everyone knows that we can construct an associative algebra U of G, which is defined as the quotient of the free algebra T of G divided by the two-sided ideal generated by elements of the form X tensor Y plus minus Y tensor X, which depends on whether we have a super or not. So it's also can be the sign property in the super case, minus XY. What we know about this algebra? So in a certain case, which I will explain in a few minutes, it will have the same size of the symmetric algebra of G. It's called the Poincaré-Bergot theorem. We know that first it's associative. Second, it has a unit, right? So it's okay, associative unital. The unit is just one, and it's not, in general, it's not commutative, of course. Second, it's also co-associative. And there is a co-multiplication, delta, which is generated as follows. So delta of X equals to 1 tensor X plus X tensor 1 for any X in G. And then we extend this by use of the compatibility with the product. So delta AB equals to delta A times delta B for every AB in UG. So, and this is, and here there's also a natural k-unit, which is just a projection to the zero term. This co-multiplication isn't indeed, it's co-associative or associative, but it's also co-commutative. So, is there any problem which I cannot face? Can I continue?
Yeah.
Okay. So those elements in the universal invariant algebra for which delta of X equals to 1 tensor X plus X tensor 1 are called primitive, and one can show that primitive elements only those are those which belong to G. So there is an interesting example, nice example, particular example of a universal invariant algebra. Suppose V is a vector space. So let's take as G the freely algebra. So it's freely algebra generated by V. So the freely generated by V. Actually, it looks as follows. So in it's naturally n-graded. So in degree 1, we put V. In degree 2, we put all brackets without any restriction. So actually it's delta 2 of V. In degree 3, we put all triple brackets. Open 3 brackets, modulo the Jacobi relation, and so on. So it will be smaller than all brackets, of course, because we should model the Jacobi relation, and so on. So it's actually it's infinite Z-graded algebra, n-graded in this case. So if you take U of G, you guess what do we get? So it's a freely algebra. So the universal invariant is a free algebra, is an associative algebra. So it's natural to guess that what we'll get will be just a free associative algebra generated by V, right? So it's a well-known result. And here the associative, so the co-multiplication is also generated by the same formula. So delta X equals to X tensor 1 plus 1 tensor X. But now we can say that it's for any X in V. But then if you look at all elements for which delta X of this form, for all primitive elements, you obtain precisely the embedding of the freely algebra into TV. Now, one can show that the dual, if you take the dual to UG, as I already said, the co-multiplication is usually due to usual multiplication. The co-associative is due to usual associative. If you take the dual here, we'll take T of B star together with some product which must be commutative, because from this you can see that the coproduct is commutative. You can easily exchange the first and the second argument. And will be another commutative operation on TV star. And this operation is called as a shuffle product. So TV star, this gives a shuffle product. Actually, it's a very interesting object which is related to many things, for instance, to iterated integrals and to other objects kind of well studied. Now, let me remind you briefly what is the size of the universal enveloping algebra. And this is called the Poincare-Birgov-Witt theorem. And I will show this in the form which I like. So assume that G admits a countable basis then there is, in general, there is a map which always exists from the symmetric algebra of G to the universal enveloping algebra of G, which sends X1 symmetric product. Let's call this like this. Symmetric product with X2, so on symmetric product with Xm to the symmetrization, it's called the Veil form, to the symmetrization of all possible products of these elements inside the universal enveloping. And here we put the sign, which in the super case, it's precisely the Kashul sign in the super case. Times X sigma 1, and so on, X sigma M inside the universal enveloping. Now, suppose the first condition is satisfied, so G admits a countable basis. So if one is satisfied, then one can show that actually this map, which is called Poincare-Birgov-Witt map in the Veil form. So this map is actually not isomorphism of vector spaces, but it's even more. So one can show that this is also an isomorphism of co-algebras. So here, as you know, we have a co-algebra structure. Here we can introduce the same co-algebra structure, which is delta x. Delta of x is x tensor 1 plus 1 tensor x for every x in G. So they're looking the same. However, they extend it in a different way because the product is different, and the extension of delta from elements of G uses the product inside UG. So we have the same formula for primitive elements, then we extend in a different way. But if we use the symmetrizer, the Veil symmetrizer, it becomes an isomorphism of bialgebras. So it's an isomorphism of bialgebras. Sorry, not bialgebras, co-algebras. And it's an isomorphism of algebras if and only if the Lie algebra has a zero bracket. So the universal enveloping must be commutative because this algebra is commutative. So this algebra is commutative. This algebra is not commutative. So the Poincare-Birgov-Witt map cannot be an isomorphism of algebras. However, both co-multiplications are co-commutative, and this map is an isomorphism of co-algebra. It's kind of nice thing about the Poincare-Birgov-Witt, so I really like it in such a form. And now one can even generalize this, and it's in this more general form. It's Also, it will be used later to show what is the Harish-Chandra pair. So everything's fine? Okay. So suppose we can also decompose G into the direct sum of H and M, where H inside G is a subalgebra, is a Lie subalgebra. And M is just a vector space complement. We even do not require that this decomposition is reductive or anything of that sort. Just any decomposition of G into the sum of some subalgebra and some vector space. Then we can write a map from U H tensor SM to U G, generalizing the above map. So with the send A times X1, so on symmetric XM, where this is an element in U H, and this is an element in SM. We send it to A times the symmetrizer, so the sum S and SM 1 over M factorial X sigma 1 and so on X sigma M, and possibly with a sign, the Cauchy sign. And one can show that this map, first of all, it's again an isomorphism of co-algebras. It's an iso of co-algebras. And also it's an isomorphism of UH modules, where this UH acts here just on the first vector, and here just by multiplication of elements on UG. So it's also an isomorphism of left UH modules. Okay, so this generalization, it's just straightforward. I never seen actually in literature correct verification, but it's kind of folklore fact. I wouldn't say it was. I just don't know the literature to refer to this. So let's now continue. So so we now we'll proceed with Lie algebras with some particular property, namely Z-graded Lie algebras. So G is called Z-graded if G is the sum of G I parameterized by Z by integers. So it's a Z-graded Lie algebra. Such that the bracket has degree 0. So this is the bracket. Has degree 0. So if you take the bracket of elements of GI from GI and GJ, it will take values in GI plus J. So now, what kind of examples do we know? So there are many nice examples. There's one good example how to build. So suppose we have one graded Lie algebra or one super Lie algebra, then we can build T shifted by 1 of G, which is the sum of G plus G. We have put here everything in degree 0 and this one in degree -1. And the bracket is organized as follows. So on elements of degree 0, it's the odd one. Here it's the joint action. And here the bracket is 0 because there are no elements of degree -2. Also, the reverse of parity of G for any graded Lie algebra is another example. And for instance, there's also nice example. There's a bench of graded Lie algebras used in differential geometry, for instance, in Tanaka theory, Tanaka prolongation theory, and prolongation of G structures, all this stuff. And the simplest example is just SL2. When we talk about the graded case, we do not necessarily mean that there's any sign rule. So, so the sign rule can be trivial. So we always assume that the algebra can be super, but this does not mean that elements of odd degree are necessarily odd in this super gradient. So it means that super gradient and Z gradient are compatible. But here, for instance, there is an example of SL2, which is purely even. So it consists of elements E, F, and H with the known commutation relations, right? So H with E is to E, H is F is minus to F, and E and F gives us H, right? And now we can put E in degree 1, or we can put it degree 2, it doesn't matter, F in degree -1 and H in degree 0. What we'll get will be Z-graded Lie algebra. And there are also all simple algebras used in differential geometry, they're naturally Z-graded, and they're even. But they're also super version of them. Now, the next question can be, the next question, can we apply the universal event Penn algebra pointer to this? And the answer is yes. So there actually nothing changed. We can consider U of G, and it will be Z-graded associative algebra, associative and co-associative, associative algebra, it will be associative, it will be a Z-graded Hopf algebra. Now, so that nothing changed here. So actually everything works nice. And in particular, in the case where every GI has a finite dimension, it's possible. Then it satisfies the property, the above property, the star. I mean, the whole G will admit a countable basis because we can add all bases for all finite dimensional GI, and we'll get a countable basis for the whole G. So it means that in this case, the graded algebra will satisfy the Poincare-Bergov property. And
graded, because I have Gaussian.
I mean, here in the free case, or what?
Okay.
In the free case, this will be in degree 1, this will be in degree 2. The triple brackets will have degree 3, but the Jacobi also has degree 3. So it's the quotient will be well defined. So the quotient will be still as a grade n grade. Okay, and now I want to explain the way how we can integrate pairs of Lie algebra and Lie subalgebra by use of Harish-Chandra pairs, and how this can be applied to the Z-graded case. And this leads to the notion of Z-graded manifolds, which we developed with Vladimir Sannikov, because it gives a natural analytical framework. So, okay, let us. So suppose we have the following pair, H and G, with H is a Lie subalgebra of G. And suppose So now the question arises: how can we integrate the pair into the pair of Lie group and Lie subgroup? So, and suppose we can do a part of the job. For instance, it's always the case when we consider super Lie groups, where this is the whole super Lie algebra and this is the even part. So suppose assume that we integrated H, the Lie subalgebra, to a Lie group. H together with the action on G. It means that H is acting on G by use of the coadjoint action. And now suppose we can integrate the subalgebra into a Lie group. Not yet the whole Lie algebra, but only the subalgebra. But we integrate it such that the action of G of H and G is also integrated. So this exponentiated. Then we can construct a certain Hopf algebra, which can be viewed as functions on the integration of the whole G in a certain way by using the purely algebraic construction. So the second, this one. So we construct the algebra as follows. So let's take homomorphisms over UH from UG to algebra of functions on H capital. So this, okay, maybe do not confuse with this H. I will use, for instance, A. Right. So A, this is the space of homomorphisms over UH from UG to the functions on H, where UH, the universal inventing, is acting on UG just by the left multiplication. And here we extend the action of H Gothic to H capital by left invariant vector fields, and then the whole UH will be acting on functions here. And then we consider the maps which are invariant with respect to such a module structure. Then we'll see the size of the space of functions. It's called a Harish-Chandra pair integration. And then I want to see. I want to show you that this space can be endowed with multiplication, co-multiplication, co-unit, unit, co-unit, all the structure which make this into a Hopf algebra. And this Hopf algebra can be viewed as the space of functions, algebra of functions, on the integration of G, of the whole G. So it works as follows. So let me erase this. The technique of Harish-Chandra pairs was developed by Bertrand Constant. The very end of 70s for integration of super Lie algebras. So just again, A is the space of homomorphisms over UH from UG to the functions on H. Right? So this can be viewed, an element here can be viewed actually a function of H and A, where H is an element in H capital because it takes values in functions on H, and A is an argument here. A is an element in UG. Now, there is a co-multiplication in the universal enveloping, so let's use it. So let's take UG, take the co-multiplication map, UG cross UG. Now, if you apply a map psi here, we obtain an element in FH cross FH. And then we use just the usual multiplication here. We'll get an element in FH. This is the way how we obtain multiplication of two functions, and then the multiplication is slightly more complicated. So let's take let's see how delta psi viewed as a function of two arguments acts on h1 a1 and h2 a2, where h1 h2 are elements in H capital, and a1 a2 are elements in universal development of G. So it looks a little bit weird, but the idea is very simple. We are trying to multiply H, A1, H2, and A2, whatever it means, and then try to exchange A1 and H2. How it will work? If you multiply A1 with H2, it's the same H2 with H2 inverse applied to A1. So, and this gives the right answer. This is psi applied to H1, H2. But now everything makes sense. So this is H2 inverse applied to A1 times A2. So, and one can show that this map will satisfy the property of co-associativity. It gives a co-multiplication, which is co-associative, not in general, not co-commutative. And if you combine all maps together, I didn't write the antipode, but it's also it's kind of obvious what should do. We should also exchange them, take here antipode here the inverse, and try to get back. So all these formulas are intuitively very clear. So, and if you combine all the properties, we obtain a Hopf algebra, which gives an integration, certain type of integration of G. What kind of integration it is? In general, it's not. So, for instance, if we take here this graded Lie algebra as G, and for instance, the Cartan subalgebra as H, which is only has only this element of the basis, and try to integrate using this procedure, what we'll get will be not SL2. It will be kind of funny object, and I will show you just in a minute what it means. So how is it related to the regular integration? Suppose we can integrate. G, the whole Lie algebra in a regular way. So find the Lie group such that its Lie algebra is G. Then we'll see how one integration is related to another one. So assume that we can also integrate G such that H will become a subgroup of G, a Lie subgroup of G. Then, let me draw the picture. Suppose this is G, and this is H inside. Now let's take the formal neighborhood of H inside G. So take the formal neighborhood of H inside G. And what we'll get will be exactly so the algebra functions of this on this group. It's a kind of group. It's not really a Lie group in general, but it's kind of it has a kind of group structure. If you take the algebra functions on it, you'll obtain precisely this sort of Hopf algebra. Now, sometimes it gives as you see in many examples, the integration by use of Harish-Chandra PS does not give the answer that we can expect, right? Because the integration of SL2 will be the Lie group SL2, but what we can get out of the pair Cartan subalgebra and the whole algebra will be just the formal neighborhood of the Cartan subgroup in SL2. So it's not exactly what one can expect. However, in some cases, indeed, it is it gives the right answer. So for instance, in the case of a super Lie group, the integration is just one of the two equivalent. So one integration can be given by use of the Fantor points, and the other one by use of Harish-Chandra pairs, and they will give the same result. So sorry, again? Yes, yes. Yeah. This will be preserved, of course. So suppose G is a super Lie algebra. Then G is the sum of G even plus G odd. And let us take as H precisely this part. Okay, so this is a subalgebra. It's an even subalgebra, and which we can integrate by use of the usual procedure, right? So if it's finite dimensional, we just integrate the finite dimensional algebra. So H can be integrated to some H, which will be G even, the bosonic part of G at the end of the day. Then if we apply the Harish-Chandra technique, we obtain precisely the correct G, simply because the direction, the odd direction, the formal neighborhood, so the Harish-Chandra pairs will give the correct G. Because the formal neighborhood of H inside G will be the same as G. All transversal directions are nilpotent. And then the formal power series is the same as polynomials, the same as smooth function. So it gives the right answer. Now, let us apply the technique of Harish-Chandra pairs. So our original point, we started thinking about this, was how to integrate a Z-graded Lie algebra by use of Harish-Chandra pairs. And in the Z-graded case, it's always possible to, I guess it will be used. Now, let me. So we'll see what happens if we apply the Harish-Chandra technique to Z-graded case. So suppose G is Z-graded. It means that G is the sum of Gi or I from minus infinity to infinity. And we can decompose in such a way. So this is G0, which later will be H, our subalgebra H, plus the rest M, where M is the sum of all components of degree not zero. This decomposition is even reductive, but there's something we don't really need. So now let us apply the Harish-Chandra pair technique exactly to this pair. So apply Harish-Chandra to the pair G0. What do we get? So the correct algebra, if I use the very general formula, is just homomorphisms over UG0. Okay, this is the most general way of UG taking various functions on G0, where G0 integrates G0. It's just the usual Lie algebra, maybe Lie super algebra, but at least we know how to integrate it. So sometimes, if this is also a super case, we need to apply the Harish-Chandra pair twice. But here, assume that everything is simple. I mean, G0 is even. So it's the simplest setting. So now let us look at this expression. So this is the same as homomorphisms of UG0. Now let's represent UG as UG0 times, so this is UG0 times the symmetric of M, right? And here we use the Poincaré-Bergouin theorem in the Weil form, right? So this is precisely what was written here, right? So not here. Was it erased? Yeah, probably. Okay, that's the Poincaré-Bergouin theorem in the form where we have a subalgebra, and then we can show that the whole universal development is as a coalgebra. It's isomorphic to UG0 times the symmetric of M. So they're isomorphic as coalgebras. And if you remember, in the multiplication, the co-multiplication only here was used. So in principle, we can freely replace this with UG0 and Sm. Now, and this takes values in functions on G0. Now, let's try to estimate the size of this space, right? If you take homomorphism over UG0 of UG0 times this, it's a free UG0 module. If you take O invariance, co-invariance, we just get rid of UG0, and this will be isomorphic as a space, and even as an algebra, because the multiplication here will be the same. Homomorphisms over R, or in general, some field from Sm to f of G0. Right? So it looks like we have dual maps on the symmetric of M, taking values in Fg. So how large is this dual? So the idea that we always take the graded components, the graded version of it, and then if you do this correctly, we come to the notion of Z-graded completion, which actually I explained in February when I gave a talk here. And I will just very briefly repeat it. So this is why actually we developed the whole technique of Z-graded manifolds, just to see how it works here. So let's take let's take M. Let's forget for the moment that this is coming from Lie algebra. So this is the sum. It's a Z-graded vector space where all components have non-zero degrees. Okay. So and this is a module over. Assume that this is a module over free module over some commutative ring. So let's take the symmetric M over some commutative ring R. In general, in this case, it will be functions on G0, for instance. Then this will be it will be commutative or supercommutative or supercommutative R algebra. And now even if GI, or in this case MI, is finite dimensional for each I, if you take the symmetric algebra, it will be no more, so the graded components will be no more finite dimensional. Because for instance, if you have elements of degree 1, -1, 2, -2, and so on, that then x1, x-1, x2, x-2, times x-2, and so on will all have degree 0. And this can be infinitely many if you do not stop, for instance, if the degree does not stop here, and even if it stops, for instance, even if it has all positive degrees and only one negative, which is even, it still be infinite dimensional because we can always compensate any positive degree by something in negative degree in some power. So it means that this is commutative, but the graded components are not finite dimensional in general. Now, if we take, to use this now. Now, if we take the dual, it's going to be awful because everything is infinite dimensional, the question how to produce the dual space. And we also have to use this for as an algebra of functions on a group which will be an integration of z-graded group. So at least we should be able to estimate the size. And then there is the following simple idea behind of that. So let's take S m star. Let's consider the filtration Fp of Sm star, which is the ideal generated by all functions of degree greater than p, and p is supposed to be greater than 0. So it will be a decrease in filtration. And let's take the completion of Sm star by use of this filtration. So this is the inverse limit of Sm star divided by Fp, or p goes to infinity, Fp of Sm star. So it's kind of power series, but formal power series, but it's like somewhat more complicated than the usual power series. I probably don't have time, but I guess in February I explained why it's so. So if you take the projective limit of that, so the completion with respect to such a filtration, one can show that this will be precisely Sm star in the graded case. So kind of yeah, it's not complicated to see, but for that we really need to use such a filtration. And actually, to be right, we should use also the co-filtration of the corresponding co-algebras and see that they are finite dimensional. Then the limit will give what we need. So it means that when we look at that, we'll see that the algebra, so this algebra will be precisely the algebra of functions on G0 cross M. And these functions will be what we expect. So this will be the formal completion of the symmetric algebra here. So this is the algebra of functions which we have in z-graded case. Okay, and now I think I don't have too much time. So 10 minutes, right? So I want to explain now very briefly how it works for algebroids and groupoids. So let's consider so now we switch from Lie algebras to Lie algebroids, or in general, Lie-Reinhardt pairs. A Lie algebroid, it's, so let's call this L. So Lie-Reinhardt pair is the one which generalizes this. So it consists of a base manifold M. L is a vector space, the sections of which are supplied with a bracket, Lie bracket. So and there's also the anchor map, which is the map from L, the bundle map from L to Tm, such that the bracket of two sections S1, F, S2, it generalizes the well-known formula for vector fields. So if there were vector fields and this was a function, it wouldn't be just application of a vector field to a function times S2 plus F times the bracket. In this case, we have to use the anchor map. So this is rho of S1 applied to F, S2 plus F, S1, S2. And one of the basic examples here is precisely Tm, right? And the rho will be the identity map. It's called the standard Lie algebroid. If you have a Lie algebroid, we can do the same trick as for Lie algebras. We can construct it's universal enveloping algebra. That now it will be a universal enveloping algebroid. So if L is a Lie algebroid, we construct its universal enveloping algebroid. And this is one way of generalizing Hopf algebras, because the universal enveloping algebroid will be generalization of universal enveloping algebra, which is a Hopf algebra. But there is another way of generalizing them. Is the following. So suppose G is a Lie groupoid. So it means that there are two maps, G, the source and the target maps to the base manifold M. There is a map which is the product, which is a map over M. It means that we can compose only elements such that for the first one, the source is the same as the target for the second one. It's a map from G. There is also the inverse, which invert two elements and exchange the T and S and so on. If we look at functions on this groupoid, we obtain another generalization of a Hopf algebra. It will be a Hopf algebra, but it will be another generalization. What is interesting that in contrast to the previous case of Lie algebras, universal enveloping, in the universal enveloping algebra case or in the Hopf algebra case, the two structures kind of do to each other. If you take the dual, then Hopf will become again Hopf. Maybe we'll need to apply completion of the product, but will be still the same sort of properties. But if we do this here, we'll get two completely different sort of structures. And in one case, the co-multiplication, it maps from the universal enveloping algebroid to a certain subspace in the tensor product. It's not really a usual co-multiplication. And here, it will be very similar to the Hopf algebra, but we should take care of TS, which will give actually two types of left and right units and so on. So we should really take care of them. The difference between the Lie group and the Lie groupoid. And now one of the basic examples of a Lie groupoid. Okay, and then the question which we ask is the following: can we apply Harish-Chandra technique in the case? Sorry. Which one? This. Okay, which one? About SL2. Okay, so can I raise this? Okay, thank you. So, what the question which we ask is the following: can we apply also the technique of Harish-Chandra pairs to Lie algebroids and Lie groupoids? And this can be actually, if it's possible to do, this can give one of answers how to integrate a super Lie algebroid. And then, in general, the answer seems to be complicated. So there is one approach which is kind of in progress. But what we did, we constructed a simple, the simplest possible answer. I mean, the simplest possible example of that is the following. So suppose we have, suppose G is a Lie algebra acting on a manifold M. Then we can construct what is called an action Lie algebroid. So it's a vector space, it's simply G cross M. So the anchor map rho will send an element X in G to the corresponding vector field. And then we extend the bracket from let's call it flat elements here, which are just elements in G, to whole sections by use of rho, by use of the property of the Lie algebroid. And this algebroid is called an action Lie algebroid. So one can do the same technique. One can construct universal enveloping Hopf algebra and try to integrate. And if we integrate, what we'll get will be an action Lie groupoid. So it will integrate just the reaction of the corresponding Lie group on M. So suppose we have the following situation. H is the Lie subalgebra of G. Then let's call this LH, which is the product of H times M. And this is a subalgebroid with the same base of L, which is the product of G cross M. And suppose it's possible to integrate the first one to a Lie groupoid. So suppose it meets an integration. Then we found a formula which is this kind of straightforward generalization of the usual Harish-Chandra pairs, which allows also to integrate the whole G cross M. So it's a kind of, I never saw it in literature, but actually it's in the same spirit as this one, but we should stick, of course, more structures inside. It's written in the paper. I don't want to write formulas because they're pretty long, but the idea is really similar to that. And the question how to do this in general, it's a kind of complicated. So I have some idea, which implies the infinite jet algebroids and some sort of structures here, but it's not developed yet. So that's I'm saying about what is known. Okay, so this is all for today. Now I guess it's a short time for questions.
The question related to SL2. So that is, of course, you say that as Z-graded as 0, right?
Yes.
But you can also thinking as a Z3 graded, right?
Z3?
Yes. Because on
this, you mean there's 3 terms?
That the SL2, because that is one minus, how to say? Yeah, that's it, minus a plus on 0 and 1. So that's a model.
Yes, yeah, minus 1, 0, 1, yes.
Yeah, so that one, so that is, you can think in terms of Z3, right? Z3 graded now.
Z3?
Yes, so that's we cannot think that's Z3 graded.
It's particular, it's truncated Z, I would say.
1 plus, how to say? Anything plus 1 here, that's a Z3. Because there's 3 elements here. So that 1 plus here is
the bracket of 1 and 1 will be 0. Because the bracket of E and E is 0, F and F is 0, E and F is H, as it should be. I think we cannot do much more with this example, probably. But do you have any examples with some other gradient?
The thing that because I was a lot with the Z and gradient, so I that is the example because that is the only you have the you put the not the only so Z3 is a does not have 3 elements. That's the 1, 2, 3 here. Then that's
but this 3, you mean really the cyclic?
Yeah.
Are you sure? So
yeah, so that's a 1 plus 1.
E and F is H. Okay, F and but F and H is F. F is H is F. H is F. It's not E.
Yeah. Okay.
But you mean you probably maybe SO3?
No.
But if you take SO3, it will be probably the form. But if you take SO3, so 1, 2, 3, 2, 3, 1, then maybe it will be cyclic. It is what you mean? Instead of SL2, we take SO3.
So
okay.
So
but
that's the next question.
So
that's of course because I was so I think mostly it's VN graded, yeah. And it's like for us, of course, we also consider the VN, but M equal infinity. In that case, is much simpler, more simpler than VN. So so that's only thing what you use Z graded and cannot extend to Z even Z2, for example.
Not that I consider. Actually, I had an idea to consider that. There was some original paper of Valentin Lechagin from '95 where he had actually invented this. He considered this sort of gradient, and he showed a very funny thing that Zn graded in Zn graded, but here Zn means Z to the power n. It's another case. Zn graded algebras which are commutative in the Zn graded setting can be non-commutative in general. For instance, he treated matrix algebras like this and quaternions and so on. And then this was developed to a certain extent by Valia Ovsienko, and he also gave this to Norbert Pansan and also with Grabowski, they work on that. So it's actually a part of the grant we wrote here a question to use more general gradients, but no one worked on that yet.
You also consider, I mean, not over complex. Over complex is easier. You not consider Z grading, and using Z grading, you.
Yeah, it can be. It can. The question can we get something, anything interesting out of it, but it worth looking at. So of course. Yeah, it can. You said Wimber triple?
Yeah.
In the case of the cyclic or what?
Complex as the varieties to understand structure. The varieties certain part and the from the varieties.
Actually, there is another nice story which is related to, which was in our, discussed in our paper, but I didn't say a word about that. So again, just if we integrate a graded Lie algebra in a different sense, right? For instance, we can integrate SL2 to SL2 capital, right? It's another way. And one will be a formal neighborhood of Cartan in a big one. And the question, in which sense SL2 capital is graded? Because if we integrate something graded, the result must be graded. There should be certain definitions which gives the gradient. And the answer is kind of very simple. So if G is Z graded, it means there is an Euler vector field which gives a gradient. Each GI component it gives precisely I, and it's a derivation. And if we have a derivation of a Lie algebra, we can integrate this to some infinitesimal automorphism of the Lie group. It's a very particular case of one East isomorphism, but here it's much easier. It means that there is some vector field here which is multiplicative and which can be viewed as a Euler-Lagrange field like in the global picture. So it's easy to see what it is. It's precisely the generator of the Cartan subalgebra. In this case, it's pretty simple. But then there is another definition of Z-graded manifolds, global Z-graded manifolds, which goes back to Ted Voronov. And he said that Z-graded manifold is a supermanifold together with some vector field, such that our manifold can be covered by local chars, and each local char, this vector field, looks like an Euler vector field. This is the sum of with some weights xi d by dxi. But over overlaps, there is some gluing. And there are many examples, for instance, where these weights are different. So for instance, we can take the projective space at 0 at infinity, and this will be different gradients. So it's a nice trick. If we integrate a graded Lie algebra, as I said before, by using Euler vector field and then multiplicative Euler vector field, what we were able to prove that it satisfies this property of Ted Voronov's Z-graded manifolds only in the neighborhood of the, in this case, Cartan subgroup, in general, the integration of G0. Then if you take the neighborhood, that indeed in this neighborhood, it can be covered by open chars, but it has the Euler-Lagrange form. And the question, is it true, for instance, in global? Because the integration of a graded Lie algebra using this global picture with to some super Lie group together with some Euler vector field, it's very natural. If we have a graded Lie algebra, then integrate the natural procedure, that what we obtain should be the graded manifold. What else, right? If it's not, then probably the definition is not correct. And then the question, what are the properties? So that's something we did not check yet. So we have only this neighborhood picture. It's another story. And what you said, it's yeah, it's a part of the whole project, right?
Next year you should explain.
Exactly. Right. So I will visit Janusz Grabowski in November. Probably we'll talk also about that. So
of course, every year you get at least one thing. So is there some more questions? Yes, please.
Exactly, yes. Fourier series? This will be, I'm not sure about Fourier series, it will be some formal power series. You want to think as Fourier?
Yeah, I would like to see equation.
Mm-hmm. Okay. Mm-hmm.
Well, I would like to think of equation.
Yes. They always like that. No, but it's always a formal neighborhood of subgroup inside the big group, if you can integrate the big group. It's always like that. If you can integrate the whole G and G0 into a group, a subgroup, the result will be functions of the formal neighborhood of G0 inside G. It's always the answer. It's always like that. Or whatever G0 and G you take. Or H and G. Yeah. For instance, yeah, this is one-dimensional subalgebra, right? Here is the cartan, which is one-dimensional. Yes, all this related to differential operators, of course. Sure. Okay, you're welcome to ask later if you have some ideas.
So is there some question? If there are no more question, let's